Good afternoon, everyone. I'm Siqi and I'm a postdoc from Norwegian University of Science and Technology Nanomechanical Lab. So today my topic is nanomechanical studies of additively manufactured high-entropy alloys. So to start with, I will give a brief introduction about the metal additive manufacturing and why we use nanointention to study the mechanical properties in MAM. And then I will show you a case study about the nanomechanical properties of the additive manufactured high-entropy alloys. And last, I will draw some conclusions in a nutshell. So, as we all know, the metal additive manufacturing has been a very attractive manufacturing method with broad application prospects because it offers several advantages, such as the fast fabrication and the great chip design freedom. And the metal additive manufacturing has many unique characteristics. For example, during the AM process, the material experiences very complex thermal history involving the repeated heating and cooling and fast cooling rate. As a result, the structure and the properties would be quite different from those obtained from the conventional manufacturing methods. Therefore, it is of great value to start to gain a fundamental understanding of the mechanical property and the deformation mechanism for the additive manufacturing materials. Actually, in most of the research, the conventional testing methods such as tension, compression has been widely used. But why we use nanointention in metal additive manufacturing? The first is because of the features in additive manufacturing materials. For example, for some non-uniform microstructure and properties, and also for some small components or complex shape, the conventional testing methods are not applicable anymore. And on the other side, the nanointention has its own advantages. It can not only obtain the small-scale local properties, but also it can obtain the deformation mechanisms at nanoscale. Furthermore, the nanointention is a time-saving method, and only very small specimens are required during the tests. So a brief introduction to nanointention. The nanointention technique applies the indenter into the surface of the sample, and then with both the load and depth are in the nano or micro scale. And as can be seen in this image, we can see that the load and the displacement are recorded during the process. So it gives the real-time measurement of the load and displacement. So we can, from this load and displacement curve, we can analyze the mechanical properties, and the elastic modulus and hardness are the most common studied mechanical properties. And besides that, the creep behavior, strain rate sensitivity, strain behavior, and the structure toughness, and so on, can be also studied by this method. And now let's move on to our study regarding the nanomechanical property of the additively manufactured high entropy alloys. So what are high entropy alloys and why we say that it's quite interesting? As we all know, the conventional alloy are made by adding small amount of secondary element into the primary element. But differently, the high entropy alloys contains at least 4 elements in an equal or near equal atomic percentage. So in this material, it has the high configuration and entropy property, and also the sluggish atomic diffusion and the large lattice distortion property. And in the previous study, the high entropy alloy has found that the the frag toughness and yield are quite higher than other materials. Furthermore, there's also other properties such as the good creep strength and the excellent wear resistance. So it has been attracted lots of attention in recent years. So in this study, we use this kind of high triploids manufactured by Lens with a single phase FCC structure. And in this study, we use two different samples to study the heat effect of heat treatment. One is the experienced one, and the other is the heat treated one. And the microstructure was studied by SEM, and here from this figure we can see that the microstructure of the additive manufactured hydrogen contains the columnar grains, and some small particles can be observed. And also from these two EBSD results, we can see that the average grain size of the heat-treated sample is a little bit smaller than the printed one, but both of them are much smaller than the custom high triploids that's reported in the literatures. And then we choose three representative grain orientation, 111, 100, and 101, to study the grain orientation dependence on the hardness, elastic modulus, and the creep behavior. So let's have a look at our results. For the hardness and elastic modulus results, we found that there are the grain orientation dependence on both the hardness and modulus. And the tendency for these two properties are same. That is, the grain 101 has the highest hardness and the modulus, and then followed by 111, and then 100. And the possible reason for it might be the change of the dislocation density during the AM process. And if we compare the results between the two samples, we found that the heat treatment can increase the hardness and elastic modulus. And that might be because of the increase of the degree of short range order domains during the heat treatment. Another property we are interested in are the creep behavior. And from this holding stage, we can obtain the creep displacement as a function of creep time. And we can see that in this curve, there are two distinct stages. At the first stage, the creep displacement increases rapidly, and then the increase rate tends to be a constant. Then it tends to the steady state stage. From this stage, we can obtain an important parameter, which is called the creep stress exponent. It can be regarded as an indicator of the creep resistance. That is, the larger the creep stress exponent, the stronger the creep resistance. So we plot the distributions in different samples and different grain orientation. And we found that in the printed sample, there is a strong grain orientation dependence. But in the heat-treated one, this grain orientation dependence is not as strong as the printed one. But both of them, in both samples, the grain 11 has the highest N value. That means that grain 11 has the highest creep resistance. And we found that the N values in heat-treated sample is smaller than the printed one. So we can conclude that the heat treatment decreases the creep resistance and the creep anisotropy. If we would like to further understand the creep behaviors and estimating the creep mechanism, there are two indicators. First one is the creep stress exponent And the second one is the creep activation volume. Because the creep is thermally active with the behavior. And as you can see in these two tables, different values indicating different creep mechanisms. And then we plot then we summarize the results of these two indicators in different green orientation and samples. And then we found that the lattice diffusion is the dominant mechanism in these two samples. So my conclusion is that nanoindentation is quite a powerful tool for investigating the mechanical properties in AM and understanding the deformation mechanisms. And in our current work, we found that the green orientation dependence on hardness, elastic modulus, and creep behavior, and the dominant creep mechanism of the additive manufactured high AAA is the lattice diffusion. And in the current work, we found that the heat treatment can increase the hardness and elastic modulus. So that's it for my presentation. Thank you for your attention.
Okay, we have time for questions. Okay, Professor.
Thank you for your presentation. I have one question. I am absolutely agree that this nano indentation or indentation on hardness measurement is very big potential method for investigation of properties. But my question is, you doesn't say it about the scatter. And question is, if this Berkovich selection, this indentor is selection, if it's good selection, because point to point you obtain, I mean, a rather different results. And for engineering practice, probably can be more suitable some different shape of this indentor. For example, ball, little bit more averaged these measurements and can be suitable for engineering practice. What do you mean?
If I understand you correctly, you mean that the small deformation volume cannot represent the whole mechanical property in the material, right? Or our
You obtain a high variation depending on the location of the measurement.
You mean the deviation of the results?
Yes.
Yeah. For that's because of the nanoindentation is a very small deformation volume, so the dislocation density in different regions might vary a lot. So the results would be influenced by the microstructure property like the dissolution density and some precipitations in the microstructure. So that might the reason for it. And but from our results, we can analyze the mean value of the results and how the trend to study the difference between the different samples or different orientations to have a overview of the mechanical properties to see the tendency or the effects.
Okay. Are there any other